A couple things you want to know about the photoelectric effect to answer this problem. If you take a piece of metal, we know that there are electrons in there. J.J. Thomson used cathode rays or cathodes and ejected electrons out of them. So we know there are electrons in there. Now, if you shine a monochromatic light, let's say it has a single wavelength of red light, so about 700 nanometers. Let me make this a little longer. So it has low frequency, and that frequency of that red light, represented by nu here, if it's less than the threshold frequency, then none of these electrons in the metal are going to eject, because you need a certain amount of energy to break them away from the atoms that they're attracted to. And so Einstein and Planck, they said that the energy is directly proportional to its frequency of its photon. More specifically, the energy is equal to Planck's constant times the frequency of that light. So if this is true, if the wave is greater than the threshold wavelength, or the frequency is less than the threshold frequency, then nothing is going to happen. So let's take a look at a wave that has a higher frequency, just above the threshold frequency. Right? Then electrons are going to eject. But because it's just above that threshold frequency, the electrons are going to eject with relatively low velocity or low kinetic energy. Right? Because most of that energy from that incoming photon was used to eject the electron. So very little of it is getting transferred into kinetic energy. Right? And by the way, if you didn't know this, you want to know that the wavelength is inversely proportional to the frequency. So if the wavelength gets shorter, the frequency gets higher, which means higher energy. So these are all relationships you want to get very familiar with, not just dealing with the photoelectric effect. So in this case here, the frequency of that green light is greater, just a little bit, than the frequency of the threshold. All right, so electrons are going to eject. So the answer to part A is electrons eject with low kinetic energy, or low velocity. All right, let's move on to B. Now the intensity of the light increases. Actually, let me just keep the same color here. All right, so the intensity of the light increases. Okay, so what that means is the intensity is directly proportional to the square of the amplitude, but for illustrative purposes, let's just draw another one of these photons, waves, this green light. Okay, actually, let's just draw 3 of them. So if you have more of that light, if you have a brighter green light, for example, these electrons are not going to eject faster or with higher kinetic energy. Rather, you're going to get more of them with the same low kinetic energy. There's your answer to B. More, because you have more light, but the light that you have more of doesn't have more energy. You just, well, overall you do, because you have more of it, but each light photon doesn't have more energy in itself. But you do have more light, so you're going to get more electrons ejected with the same low kinetic energy. Right? Just again, emphasize this again. The energy is only proportional to the frequency, not its intensity. It doesn't matter. It's irrelevant how bright the light is. It only matters the frequency when you're talking about energy. Right? And B is not talking about energy. It's talking about how many, or it's talking about intensity. So intensity is related to the number of electrons. So I'll draw a graph after we're done here to re-emphasize all this. All right, part C. Now we can maybe use a blue here. So let's say we have another light with a shorter wavelength. What that means is higher frequency and higher energy. So let's say blue light. All right, so a shorter wavelength, higher frequency, higher energy. Then we're already above the threshold frequency. So we are going to get electrons ejected, but now those are going to eject with more kinetic energy because this blue light has more energy than this green light. And since both of them have enough energy to kick an electron out, more of the energy here is going to get transferred to kinetic energy of that ejected electron. So a couple graphs. So here, I'll write down the answer in part C. Part C, electrons eject with greater kinetic energy. Right, so the frequency of the blue light is greater than the threshold frequency relative to the green or the red. All right, and because this is cesium, this is accurate, I think. Cesium has a threshold frequency about in the orange or yellow light region. So a couple graphs here you want to be familiar with is in part A was asking about, what was it asking? All right, so frequency. So if x-axis here is the frequency, and we have the number of electrons, right? And let's say this is the threshold frequency. That's the minimum amount of energy before these electrons can escape the metal. Let me try to pick a neutral color here. So nothing happens with this red light, nothing happens with this red light, but as soon as you hit that threshold frequency, which for cesium I think is like yellow or orange anyway, but let's keep this green going, then you're going to get electrons ejected. All right, but if you don't increase the intensity, you're not going to get more electrons. They're just going to eject faster. So that's what this graph looks like. Now let's draw another graph where we have the same thing on the y-axis, the number of electrons, and this time we're changing the intensity, so I for intensity. All right, and so if we're above the threshold frequency, so if we're already above it, all right, so electrons can be ejected with this light, then increasing the intensity, let's just keep this green because this kind of matches the example in our problem, is going to eject more electrons. So this is kind of illustrating that scenario. The more light you have of that green, then the more electrons you're going to eject. All right, and the other two graphs you want to be familiar with is relating to kinetic energy. So not the number of electrons being ejected, but how fast these electrons are being ejected. Okay, so if you have frequency on the x-axis and there's your threshold frequency again, right? So nothing's going to happen with this red light, and then as soon as you hit that threshold frequency, in our example, let's say it was green, you're going to get electrons ejected. And you increase that frequency, they're going to eject with faster, more kinetic energy. It's going to be a linear relationship. As if you increase the frequency, the ejected electrons are going to have more kinetic energy. So it's a linear relationship once you've reached that threshold frequency. All right, so one more graph could be a kinetic energy graph. Oops. Actually, that's I think that's good here. Good place to stop.